Hi guys, this is a Productive Cloud Innovation. So we are in our second part of the series for the fallacies of distributed systems, where we are going to discuss two major areas of these fallacies. And I will turn over to Mark to describe them and enlighten us.
Fantastic. Thanks, Rohit. So before we had talked about fallacy one, which was that the network was reliable, let's talk about fallacy number two. And just in case those of you weren't listening to the prior podcast, a fallacy is something we believe to be true, but is exactly the opposite. It's not true. And these were coined in 1994 by Peter Deutsch and other folks from Sun Microsystems. Fallacy number two of distributed computing states latency is zero. I love this fallacy, Rohit, because we all know that there is such a thing as network latency, particularly when we're talking about accessing cloud infrastructure from either on-prem or even just normal computing, whether it be on-prem or cloud-based infrastructures. Either way, we do in fact have a latency. This is one of those things a lot of developers understand but tend to forget. Because if I'm going to invoke a method or a function on another class, that latency, we'll call that T for time, T local. That latency to make that call is measured in literally nanoseconds. Now that's not to execute the code, that's just to get over to that class. That's a nanosecond or so. It's just a memory switch. However, when we take that exact same call, that exact same method call or function call, and transport that across some sort of remote access protocol, any, REST, gRPC, SOAP, messaging, you name it, we have latency. And that time to make that call in network time is T remote. And the thing is, Rohit, that T remote will always and forever be greater than T local. In other words, we do have network latency. And so one of the things, questions I'd love to ask, whether I'm doing a training or a conference or at an assignment or a gig at a client, is I love asking, so let me ask you, in your production environment, round trip, for a round trip RESTful call, what's the average latency in your production environment? And you know what, Rohit? I always get silence. Because very few people know this. And so the problem is your latency for a round trip RESTful call in your production environment, not just a test environment, is it 60 milliseconds or is it 300 milliseconds?
Mm-hmm.
When we take our monoliths and we break them apart into cloud native or 12-factor applications, or even just to split them apart into like a service-based kind of architecture, we now introduce latency. And this is an important aspect from the architectural standpoint to know how am I impacting performance? So I always ask, what's your average latency? And then if somebody does find it out, I'm like, that's fantastic. So what's your long tail? In other words, your 95th to 99th percentile. Because you may have 47 milliseconds average, but your long tail, your 95th percentile, is upwards to 800 milliseconds. Now that's almost a second, and you haven't executed one piece of code. That's what that latency piece really means, and we do have it. So latency is not, in fact, zero.
Yeah, so I was looking around, and there is a site like wondernetwork.com which actually thinks it tells like New York to London one way is 58.95 milliseconds. So you're making a round trip call for any call we are making out for 120 milliseconds. Yep. So to say that, one of the things which comes in, how should we design our application, from services which we have got, microservices, service orientation, how should we do that so that we can fix that issue?
Well, one thing that I thought of when you were asking that question was, if you want to really see and understand latency, just even as an end user to your own systems, you're right. Latency significantly depends on the distance Well, it depends on a lot of things. As a matter of fact, it depends on the other 6 fallacies of distributed computing, but also it depends on what server we're hitting, the bandwidth that you have, so on. But there's a wonderful website called speedof.me. And let me say it again, speedof.me.
Mm-hmm.
And if you go to this website, what it does, it takes about a minute to run, but it determines not only your uptime or upload and download bandwidth, but it also shows your latency and which server you're talking to. I've been actually using this website, speedof.me, quite a lot, especially since we've now been doing virtual trainings, podcasts like you and I are doing, Rohit. And the point is, before we get started, we usually say, well, wait a minute, what's the overall latency that we're hitting? The reason that's significant is because, let's say I'm asking for information. Let's say we have a group chat, and I'll say, so what does everybody think? Is it option A or option B? And there's silence because I'm like, oh no, I forgot to check the latency. And so if that latency is 200 milliseconds, it's taking a while for that voice to get through, somebody to respond, and then 200 milliseconds to answer that question. And so a lot of time goes by. It also allows whether we want to make a call, for example, a Zoom call to India. Really good to measure this, speedof.me, to see the latency of those networks, and whether it's even viable to have 20 people in a Zoom call, for example. But one of the ways of actually addressing the overall latency, of course, I mean, there's a lot of other fallacies we could actually talk about, but one of the ways of addressing that latency, of course, is proximity between servers. Another way is co-location of services. When we start talking about things like microservices and Kubernetes, and the Kubernetes, of course, the deployment unit is a pod, but even in a cloud-based infrastructure, if I've got a particular availability zone that I'm working in, by starting to co-locate services. And that is one way of helping to reduce the latency, because generally then it's in a local network, then that latency, Rohit, I have seen gone down from in the neighborhood of 200 milliseconds down to about 12. Mm-hmm. That's the significance. Because with the local networks, of course, with co-located services, or even co-located partitions, if we have 2 different partitions and just co-locate those, the point is, in a local network, we're bypassing a lot of the other infrastructure a network actually has. The firewalls, the switches, the routers, the hubs, all this kind of stuff. And so that's one primary way of actually reducing the latency. But there's another aspect, though, Rohit, I want to talk about with latency, because latency obviously impacts performance and responsiveness. The more we start hopping between different services within our cloud infrastructure, the more latency starts adding up. If I have 10 hops and that latency is 200 milliseconds, actually, here's a good question. If my round trip latency is 200 milliseconds, and I make 10 different hops to complete all the queries and updates I need to do for that business transaction, and then return to you, the question is this: 200 milliseconds at 10 hops, what's my responsiveness or performance hit there?
Well, it depends upon if it's async and you're doing the other calls and you're waiting on it, then, that takes care of like the customer perspective. Or it's like, that's one way I try to solve that kind of problem.
Yep.
Because this is pretty darn problem, because like, if you're making 10 hops, hey, you say that, okay, I'm going to start a process, and then that's an event-based process, let it take whatever it takes, but then you are not waiting the user, and they can still do through WebSocket, they can do other things and their technologies to make sure they get call back when the process is done, some way of doing that,
Sure. Exactly. So assuming it's all synchronous, synchronous, mathematics tells you that, let's see, to 200 milliseconds round trip average, you're making 10 hops, that's 2,000 milliseconds, that's 2 seconds. But actually, Rohit, here's the problem. It's a lot more.
More, yeah. Mhm.
And here's the reason. So I'm going to skip over fallacy number 3 because that's going to take a whole podcast in and of itself. But I'm going to go to fallacy number 4 of distributed computing. Fallacy number 4 says the network is secure. Now, we all know the network, of course, is not secure. And as we start moving to cloud-based infrastructure and breaking apart our applications, irrespective of the granularity, each one of those new services that we create and deploy on cloud-based infrastructure, is it secure or not? In other words, it's got an endpoint, whether that's a messaging or a RESTful or a SOAP call endpoint. And the point is, I have no idea because it's remote, it's distributed, who's calling me. And so fallacy number 4, the network is secure, is pretty significant to us because now we know networks are not secure. And that's why we have to apply security. But here's the problem. It really does link to fallacy number 2. Latency is 0. Because the point is this, that 2,000 milliseconds to make those 10 hops is more likely to actually be more like 4 to 5,000 milliseconds because every hop we make to a distributed service not only incurs latency, that's fallacy number 2, but also that endpoint needs to be secured. In other words, we may have to go through a reauthorization of that particular request to say, well, I know you were authorized already to make this, but now I'm hopping over to the, let's say, the wallet service to get the credit card. But I don't know who you are. This is just a RESTful call. And we may be able to look in the header or the accept header and see that there is a JWT or something, but just because that web token is there doesn't mean it's actually valid or may be expired. And so a lot of times we have to reauthorize, sometimes even re-authenticate a request.
Yeah.
It really does. I love the way these all link together because it really does link back to fallacy number 2. So 2, latency is 0, and 4, the network is secure, means not only do we have to spend extra effort and energy in securing all of our services in cloud, but also that incurs additional processing time, additional latency. And so when we start to think about performance and responsiveness in distributed systems, when we deploy to cloud and start breaking apart our applications, it's not only fallacy 2 that impacts that responsiveness, it's also fallacy 4. And again, your point that you just made, Rohit, is one way to actually address some of these issues as well, because the more we rely, if we can, on asynchronous communication, the less or the better. Let me start over because this is a really important point. I'm trying to formulate it in my head. Here's the key. The more we rely on asynchronous behavior between services, what that does is it significantly improves the responsiveness of our systems. See, that time, that latency is still there. The time to reauthorize an individual or a service call is still there, but the user's not waiting for it. And so it is one way to address that piece from a responsiveness standpoint, but now performance is still the same problem, which is why performance and responsiveness end up being joined if we have synchronous processing.
Exactly.
Very little difference of what we really can do. Now we can try to run things in parallel, but my point is that asynchronous allows us to respond faster to the user to take care of the fact of, I have to resecure all these 10 endpoints and I don't want the user to wait for those. And so it's one way of actually addressing that issue. So the two are interestingly linked from a performance standpoint.
Yeah, it's great. I think they are all working together. So, I mean, this is a great talk. We discussed just now, latency is never 0 and network is not secure. That's the key part which we are trying to say here. And of course, you need to do OAuth top 10 and threat modeling and, all those things are there. But the important thing to remember is that whenever we design a system, what's the response time we are looking for? How much the customer can wait? And what I feel is I have seen a blink of an eye is the time they can wait. Otherwise, they're going to move to another application. So that's what we are designing it for. So that really brings down to our the next fallacy we'll be discussing in our next session. So thanks, Mark. It was great
You
talking to you.
bet. All right. Thanks, Rohit.
Yeah, great.